In this truss problem, we're trying to find the forces in members BH and CH only. So we want to find what I will call FBH and FCH. We have a truss problem here. All of our joints between members are pins, and we see that loading is only taking place on the pins, and every member that makes up this structure is a two-force member. So this is going to be a truss type of problem. So what we wanted to look at first is externally, is our structure statically determinant or indeterminate, before we decide how we want to proceed. Do we want to make a section cut? Do we want to use just pins? But if we look externally first, A, we have a roller, and E, we have a pin. We're going to have three support reactions in this system, so it is statically determinant. So I'm going to first solve the external problem before I jump in and start making section cuts or pin diagrams. I'll decide how to proceed at that point. But the first free body diagram is going to be the external picture. So I have my truss at A and E. I have my supports. I'll put in these applied loads as well. So I have a couple of these 1,000-pound loads at A, H, and G, and one at D. And these are all 10 feet apart. And we will have our support reactions as well. At A, we have a roller. It allows horizontal translation, but not vertical. So I am going to have a force I'll call A at that location, vertically up. And at E, where I have a pin, I'm going to put a horizontal component of force and a vertical component of force. So knowing it was statically determinant, if I look at the free body diagram, there are three unknowns, so I will be able to solve those unknowns. So I'll move on and write some equations now, and then I will come back and draw some more free body diagrams. So in picture one, I'll start with the moment around E, so I can get one of my unknowns right away. So if I take the moment around E in this picture, EY and EX are not going to be in the equation, but I will have a positive 10 times 1,000 from the force acting at D, plus another 1,000, but times 20 for that middle force, plus another 1,000 times 30. These are all going to be counterclockwise, plus 1,000 times 40, minus 40 times A. So taking the moment at E, I will be able to find A from this first equation. Then, if I do a sum of forces, I'll start in the X direction. In picture one, I only have one force, and that's EX, so EX must be 0. And finally, I can take the sum of forces in the Y direction in this picture. And I will have A plus EY minus 1,000. I'll write them all out even though I know there's 4 of them. And there's my equation 3. Now, if I move to a solve step, so I can find what these external reactions are, from equation 1, the only thing I don't know is A. A must be 2,500 pounds. And it's positive, which means since it's an external force, my assumption was correct. It is up. And I can use, 2 tells me that EX is 0. And then equation 3, now that I know the value of A, this will give me the value of EY, is going to be 1,500 pounds. And it's positive, it's an external reaction. That means that my assumption of up was correct. So 3 external forces I was able to find using that external free body diagram. And I did that because my system was statically determinant. Now I can go and look at the internal forces. So far I haven't found anything that I ultimately need to find, BH and GH, but now I can consider on my picture where these are. So BH I'll just mark here, and GH I'll mark so that I can come up with a plan of how I want to solve this. Now, being as I only need 2 of the internal forces and not all of them for all of the members, that's a clue that I probably want to start with a section cut, and then maybe I'll need more than one, maybe I'll need a couple of steps, but a section cut will probably reduce the total number of free body diagrams and equations that I need to write. Ideally, if I can make a section cut that went through, in this case, both, or in general, all of the internal forces I need, that would save me the most work. But I also want to keep in mind my rule of thumb when making a section cut, that I want to cut through at most 3. So if we see here, can we cut through GH and BH and cut through only 3 members? We could make a cut that looks like this, that cuts through both of our members, but we're cutting through 4 members, not 3. So that is, we can make a picture, we can get equations, but we're going to have more unknowns than equations, so I'll recommend against making that cut. And that's really the only cut we could make that goes through both of our members. However, it goes through 4 total members, so I'm going to suggest a different cut where we will have to make a couple of pictures here, but any picture we draw is going to make itself a solvable system. So I'm going to instead make this cut, and then I will need another free body diagram, but at least I'm going to be able to cut through one of the members and solve for it. And notice that this cut is only going to go through a total of 3 members. So this is what I will have as my second free body diagram. Now I can use everything to the left or the right of that cut. Because there's just less happening, I'm going to do everything to the left of my cut. I could have used everything to the right. It's just going to be more to draw, so that's the only reason I'm choosing, in this case, left. So what I want to do in this picture is every member that is intact, that's in that bubble, I am going to copy exactly. And notice this bubble of the system I'm drawing here has to close in on itself. So I've looped back around, and the only members I'm cutting through are GH, CH, and BC in this case. Everything else is going to remain intact. So AB is unaffected by the cut, BH and AH. So everything about those is going to stay as it was. So I'll copy all of that stuff exactly. That 1,000-pound load is unaffected. The 1,000-pound load at H is unaffected. A, that support reaction, is unaffected. Since in the first step I already found its value, I'm going to just write it here. So I found it was 2,500 pounds up. So that gets copied as well. All right, so what do I have to modify is these members that I cut through. I can now see their internal loads because I made this cut. I separated it from the rest of the truss. So in this picture, I can see the forces that were holding the truss together through that cut. And that's what I have to model through these 3 members. So I'm going to assume tension. So coming out at the bottom is the force in member BC. I can now see the force, and it's an unknown. And here I have the force in GH. And down here I cut through CH, and I can see that force too. And I'll make that construction line here. That's a 30 degree, and this is also a 30 degree by symmetry. So I have all the dimensions I'll need, and then I want this 10 foot, and then this vertical is since this is a 30, 60, 90 triangle, then this vertical is 5.77 feet, rounded off a little bit, but I'll need that for when I want to take moments. And what I'll do also is I'll draw point C here. We'll see why it will be helpful in the equation step in a moment. But it's still a point in this picture, and FCH and FBC are going to have its lines of actions pass through point C. So we'll see what its utility is in a moment. All right, so we have this complete free body diagram. I'll put in the rest of these labels here so we can refer to them. So my free body diagram 2, again, by design, we see that there are only going to be 3 unknowns. So because it's a 2D rigid body, I will be able to solve for all 3 of them. So using picture 2, I can write new additional equilibrium equations. So in picture 2, I am going to start by taking the sum of moments around H. And what this will do is 2 of my unknowns will not appear here because CH and GH have lines of actions that pass through H, so they will not contribute to the moment. And that 1,000 pounds acting on H also will not. So I'm going to eliminate 2 unknowns and be left with just 1 unknown when I write this equation. So in the sum of moments around H, I'm going to have 5.77 times FBC. That will be positive counterclockwise around H. I am going to have the 1,000 pounds times 10 feet, also counterclockwise, minus 2,500 times 10 from the reaction at A. And that's going to be clockwise, so negative. So equation 4, I will be left with only 1 unknown FBC, so that will be easy to solve in my solve step. Another thing, now this is breaking with what I usually do to solve these, I'm actually going to take a second moment equation. To make the algebra just a little bit easier, I actually want to take the moment around C. It's not in my diagram per se, but it's still a point that exists in space, and it's a good point to take the moment about because CH and BC, those forces, have their lines of action that pass through it, so I'll be left with just 1 unknown, GH, in this equation. So I usually do 2 forces and 1 moment. We're going to see here I'm actually going to do 2 moments and 1 force. But we have to be careful when we get to the force step that we cannot take the force in the direction of the CH axis, since those are the 2 points I'm taking moments about. So we will check that and we'll be okay here, but it is an additional thing to think about if you ever take 2 moment equations. So about point C, CH and BC will not appear. We are going to have the 1,000 pound force at H is going to be, this is also 10 feet from B to C. And that is going to be counterclockwise positive, plus 1,000 times 20 from the force at A, minus 2,500 times 20 from the reaction at A. And now we're going to have 2 components of GH that are going to contribute to the moment. So we're going to have the horizontal component, which is FGH cosine 30. And its perpendicular distance from C, the horizontal, has a vertical distance of 5.77 feet. And note here, my base units are feet and pounds for force, feet for distance. Now I have a vertical component as well, minus FGH sine 30. And it has a perpendicular distance, that's the horizontal distance to C, of 10. All right, so in this equation, I have only 1 unknown, GH. So I'll be able to solve that. And finally, I will take the sum of forces. And as long as it's not along the CH axis, which is, that's not horizontal or vertical, so probably I wouldn't have wanted to take the force along that axis anyway, but we just want to make sure. So I'll just do it in the x direction. So I have one more equation here. I have FBC plus FCH cosine 30 degrees plus FGH cosine 30. So by the time I get to equation 6, I will know 2 of these unknowns and I will be able to find the third. So again, by cutting through only a couple of these unknowns, I'm going to be able to solve for all 3 of them. So equation 4, FBC is the only thing I do not know. And I can solve that as a positive 2,600 pounds. So that turns out to be in tension. In equation 5, GH is the only thing I do not know. So I can solve for it. GH is a negative 2,000 pounds. That's in compression. And from equation 6, actually the one unknown I ultimately did need to find, CH turns out to be a negative 1,000 pounds, so it is in compression. All right, so CH I found. Again, in these pictures, whether it's a section cut or a joint, I am assuming tension always. So a positive value says my assumption was correct. A positive is interpreted as tension. A negative means my assumption was wrong. It's actually in compression, and a negative then will be indicative of compression. So CH I have now found. And looking back, I realized that I was looking for CH, not GH, this whole time. But the same procedure is going to hold. I have one of my unknowns now. I have the CH. Now I still need BH. So I can make another section cut, would be one possibility. I could cut through, for example, here, make this cut. And that would be okay because it's cutting through 3 members. And one of them, BH, I'm interested in. So that would be okay. Or I could proceed with making a pin diagram, and that would also be fine. So I'm actually going to go with a pin diagram. And for simplicity, I can just make a pin diagram at B. And that will be another free body diagram. And then at the end, we'll reassess this structure. So B, if I draw this pin, I have, assuming tension, FBC coming out. I have FAB to the left. And I have FBH up. And that's everything happening at B. So actually, this is pretty simple. I have equation 7. I can just take the sum of forces in the y direction in picture B, and the only thing I'll have is FBH. So actually, really quick, FBH turns out to be 0. So equation 7, FBH equals 0. And that was the other force that I was interested in. All right, so all the unknowns we've now found. It took 3 free body diagrams, and we have them. Now let's look at a step I actually skipped that's kind of optional at the start of this, but let me get rid of some of this here. We can, before we really do anything, we can identify if we have any zero force members in our system. So let's see if we can identify any. Now, it turns out BH was a zero force member, but by inspection, could we have seen this right away? So let's go through pin by pin and see what's happening. So A, we don't want to evaluate. H, G, but they have external forces. D has an external force. E has a support, so we're not going to consider those. Let's look at C. From the perspective of point C, we have no members attached to it that have a direction to themselves. BC and CD are parallel to each other. CH, CJ, and CG all have vertical components, so we cannot conclusively say any of them are zero force members. At point J, GJ, JE are parallel, so we cannot say they are zero force, and JD and JC both have components orthogonal to the GE axis. So that leaves us with B, which I obviously saved for last, since that will we be able to identify one. It's connected to members AB and BC, so those we cannot say are zero force members. However, BH has a component of its force orthogonal to the ABC axis, which in this case is the vertical axis. So by inspection, BH, we can just see, has to be a zero force member because its force has a direction all to itself from the perspective of B. So by inspection, and as we saw by actually drawing the free body diagram at B, BH does turn out to be a zero force member. So in the end, we found CH and BH. CH was a compressive 1,000 pounds, and BH was a zero force member.